We're delighted to continue the morning session. As people come in, I suppose we can just begin for the sake of time. I've been asked to chair this session now at the last minute, so I'm preparing myself. So let's welcome Professor Divine Kumah. And you, of course, heard him speak some words yesterday at the panel yesterday afternoon. So today he's going to talk about his research. So he got a PhD in applied physics from Michigan in 2009 and did his postdoc on surface phenomena at Yale University. And now his research interests are in experimental condensed matter physics. So it kind of it's a nice continuation in some sense of what we heard from Professor Selena on this fundamental physics. So welcome, Divine.
All right, thank you very much. So I just want to start off again by thanking Bill and the rest of the organizing committee for putting this together. It's been a wonderful couple of days seeing how quantum computers work, to seeing how we need to think about connecting them, to the talks today, which are focused on the materials and the architectures which we need to actually realize some of the cool quantum computers. And hopefully in the next decade or so, you should be able to have a cell phone which can do quantum computation. All right, so that's the goal of us materials people is to make the materials that you guys are going to use to make those systems. And my name is Divine Kumah. I'm at Duke University, and I'm going to be talking about some of the experimental work we're doing in studying and understanding low-dimensional materials. So you had some talks this morning about 2D materials. I'm going to be talking about quasi-2D materials, where we take materials which are well known in their bulk form and reduce their dimensions down to the order of a few atomic layers. And in my group, we work on synthesizing these materials. I'm going to talk about how we synthesize these materials and also study all the different kinds of interactions that could occur in these materials, from structural interactions where you have two materials put on making an interface with each other, to interactions where electrons could move from one material to another material, to spin interactions where the magnetic properties of one material, when you make it very thin, can influence the magnetism in the layer which is adjacent to it. So I will focus my talk today on two classes of materials. The first one is going to be related to magnetic oxides. So I'm going to be talking about some of the materials we're making where we can make very nice atomic layers of these oxide thin films and understand, study, and investigate their magnetic properties. And I'm going to motivate why we study these magnetic materials in a minute. But I'm also going to talk about some of the work we're doing now on looking at superconducting oxides. I'm going to talk about two kinds of superconducting oxides, ones which we find in binary oxide materials like titanium oxide, and some of the superconducting oxides where you take two materials which by themselves are insulating, and when you put them together very carefully, you can actually form a superconductor at that interface. So that's going to refer to as interfacial superconductivity. Right, so nature gives us the periodic table. It gives us all the different elements which we can classify by their atomic numbers, atomic masses, and even classify them by some of their basic properties. But the story doesn't end there. If you take a material like carbon, for instance, and you've already maybe seen this example in the first talk, carbon can manifest itself in many different ways. And by what I mean by manifestation is that the carbon atoms can arrange themselves in very different crystal structures to give very different physical properties. So when you have carbon arranged in this particular structure called a diamond structure, where each carbon atom is strongly bonded to a couple of four neighboring carbon atoms, you have diamond, which is very hard, and if you have very expensive, and but insulating, it doesn't conduct electricity very well. And these same carbon atoms arrange themselves in this hexagonal pattern. You have, and then you have these weakly bonded layers. You have graphite, and you've already been introduced to that in the previous talk. Graphite has very different properties from diamond because of the differences in the way the atoms are arranged at these really, really small length scales. And then you've seen in a couple of talks here that if you can now take this material and just take a single layer of this carbon sheet out of it and make what is called graphene, there's a lot of very interesting physics that emerges. And so Pablo's talk touched on some of the interesting physics you can get from these twisted bilayer graphene sheets. And so you can go from a material which is insulating, and just by changing the way the atoms are arranged and changing the dimensionality, you can have a system here which displays really, really exotic and really interesting properties. All right, so again, referring back to the first talk, there was a good introduction to what a two-dimensional material is. So in the case of graphene, you can take a graphene flake. It's just a single layer, and you can do a lot of interesting things with it. I'm going to be talking about what I'm going to refer to as quasi-two-dimensional materials, where we take materials which are, again, well-known in the bulk, and we're going to grow them with thicknesses on the order of only a few atomic layers, so that we are reducing their dimensions along one direction, and they are periodic in the other two directions. So in making materials quasi-two-dimensional, there are a couple of things that can emerge, right? So when you take a material which is really big and you make it really thin, it's going to have a surface which is going to have a very different bonding environment from the bulk. If you make it into a layered structure, it's going to have interfaces with other materials which might have very different magnetic, electronic, and structural properties. And as a result of all these differences here, we're going to expect that the properties of these quasi-two-dimensional systems are going to be very different from what the bulk analogs of these systems are. So what I'm going to go through is an examples of how we can make these materials. We can make these form these couplings between these very dissimilar materials, and then have new and interesting properties which can potentially be used for making the next generation of quantum computers and quantum sensors. Right, so you can combine all these materials in many different ways. And as I've showed you before, the crystal structure is really key to trying to understand how these systems behave. And I'm going to be focusing first on a class of materials called the perovskite complex oxides. So they are complex because they have more than two different elements combined together in their crystal form. And they are perovskite because they have this basic structure here where you have one metal ion, which could be a transition metal ion like titanium or manganese, surrounded by an octahedra of oxygen. And then at the corners of these cubes, you have another metal ion, which you can pick from anywhere in this periodic table, but we're going to be looking at some of the materials you can get from the rare earth lanthanide series. So I refer to these materials as designer materials because you can pick by just replacing the elements in this structure here, you can have any physical property in condensed matter physics imaginable. So you can have systems which are insulating, systems which are ferroelectric, systems which are superconducting, and systems which exhibit a wide range of very interesting and different magnetic properties. So because I'm going to start with magnetic materials, I just want to briefly show what kinds of magnetic materials you can have. There are many classes, there are different classes of magnetic materials. Some of them are ferromagnets where at high temperatures, you can associate a spin with each lattice site. And above some critical temperature, these spins point in random directions. And so as a result, there's going to be no net magnetic moment above Tc. And below some critical temperature, which depends on the material system, you end up with this ordering where all the spins align in the same direction. And this is a system which I'm going to refer to as a ferromagnet. There's another class of materials called antiferromagnets where below this special transition temperature, or in this case, the Néel temperature, the spins prefer to align themselves in an up-down, like a zigzag pattern, where every neighbor has an opposite direction in which the spins are pointing. And so in the rest of the talk, I'm going to be referring to both ferromagnets and antiferromagnets, and that's going to be related to how the spins in these systems are configured. Right, so why do we care about spins? We all have magnets. Well, we may have magnets on our fridges. Magnets have been with us for thousands of years. But most recently, we are finding that we can take advantage of the spin of electrons in addition to their charges to store and process information. And so there's a whole new field which is emerging called this field of spintronics, where we can use the spin of these electrons in these systems as a way to do a lot of very interesting and very cool things. So in the rare earth manganites, again, going back to their structure, they have this perovskite structure where you have manganese in the center of these oxygen octahedra. In the ideal case, these octahedra are not rotated, but I'm going to talk about the effect of rotating these oxygen octahedra on the properties of these systems. So in what I'm showing here are what are called phase diagrams. So people many years ago have created bulk forms of these materials where, in this particular case, you can, at the green side here, you can alloy lanthanum, which has a 3+ charge, with strontium, which is divalent. And by changing how much lanthanum and strontium you put at these sites in the lattice, you can have a very wide range of physical properties. So for example, in this blue region here, where you have about between 15 to close to 50% of strontium replacing the lanthanum, the material is, in this blue region here, it's a ferromagnetic metal. And this material has a very interesting property where if you apply a magnetic field to it, you can actually modulate the resistance by a very large amount. Right, so by just changing the chemistry at these lattice sites, you can have the ferromagnetic metal at room temperature and below room temperature. You can have an insulating phase here if you get your strontium close to 0. And in this red region here, the material is an anti-ferromagnetic metal. You can also replace lanthanum with neodymium. Both of these ions have the same 3+ charge, but the effect of doing that is that you are changing the effective ionic radius, which is occupying this site in the structure. So what happens then, I'm going to show you, is that in addition to changing the charge as you go along this series, you're also effectively changing the structure. And that can lead to also changes in what the phase diagram is going to look like. So the point here is that if you take anything away from it, is that in these systems, you have a lot of degrees of freedom. You can change the charges you put at these sites, the net charges here. You can also change the structure, and that can lead to very different phases, both in magnetic and electronic phases of these systems. Right, so when you change the charge, so when you change how much lanthanum and strontium you have at those corners, you are effectively, because manganese can also have multiple charge states, you're effectively changing the ratio of manganese in different valence states. And there are many other oxide systems where this trick is used to change the properties of materials. And a very good example is the case of the high TC cuprate, where, for example, in this system here, lanthanum, strontium, copper oxide, it's a mouthful. By changing, again, the ratio of lanthanum and strontium, if you start off with just 0% of strontium, the material is insulating. It has a high resistivity at room temperature. And when you reduce the temperature, this resistivity goes up to really large values. And as you add more and more strontium, you're effectively adding holes into the system. You're doping the system with holes. And the resistance goes down. The system becomes metallic and superconducting. And this is what is shown in this phase diagram here. As you change the hole concentration, you see that you go from this anti-ferromagnetic insulating state. Anti-ferromagnetic means spins point in opposite directions. The system is a really bad conductor of current. And then at some really, really precise range of doping levels, you end up in this superconducting dome phase. Right, so in this case, you are changing the electronic, the amount of holes in the system, and you're using this as a way to tune what properties you can, that emerge in the system. The other way you can change the properties again, just a really quick review again, is that you can also change the size of the rare earth, the ions that sit at these sites here. And if you have a very large ion sitting at this corner in this structure here, where these green balls are located, those octahedra do not rotate. So you end up with these nice, perfect cubic structure. And as you progressively reduce the size of these ions at these locations, these octahedra tend to rotate to fill up the volume of space. And one consequence of that is that if you look at the phase diagram of the rare earth nickelates, so where you have nickel here and a rare earth ion here, as you move down up the rare earth ion along in the periodic table, going from lanthanum to lutetium, you're effectively changing the effective radii of the ion that you're placing in these corners here. And as you can see, you can go from lanthanum, which has the smallest rotation because lanthanum is the biggest ion in that series. Lanthanum nickelate is a paramagnetic metal. And as you decrease the size of the rare earth ion you have in the system, these octahedral rotations increase, and the system goes into this anti-ferromagnetic insulating phase. The reason this happens is that a lot of the interactions, the charge and magnetic interactions depend on the bond angle and bond distance between the transition metal ion, the oxygen, and the next transition metal ion. So as you progressively change this structure here, you're effectively changing how the spins talk to each other and how easy it is for charge to move in this system to conduct current. So in my lab, we have all these knobs we can then use to tune the properties of materials. And so the question is, how do we grow these materials very precisely? And how do we probe these interactions? And how do we design new interfaces with very specific properties? Right, so we do this by a process called epitaxy. So what we do is we take a substrate, some crystal with some well-defined structure, surface structure, and we deposit the material of which constitutes the film we'd like to grow on top of that. And if the lattice spacings of the substrate and the film we'd like to grow are not too different, just within a few percent, then the film we grow on is going to change, modify its structure slightly. It's going to stretch itself or compress itself to match the template on which you're growing. So this is like Lego blocks. If you have kits with different Duplo Lego and Lego, they have very different sizes, and you cannot really push one on top of each other. But in this case, if they're close enough, the one of them is going to stretch to fit the other template. So this allows us to change the structure of a material using this knob of epitaxial strain. And as I mentioned, we can also make heterostructures where we form interfaces and use the different interfaces we form as ways to tune the properties of these systems. All right, so in my lab, we have an MBE system here, and it's an ultra-high vacuum system. So we pump it out. The base pressure in it is in the 10 to the minus 10 torr range. So it's a very clean system. And at the bottom here, we evaporate the high purity metals, which constitute the structure we like to grow. And then so we can control the rate at which we evaporate the materials and grow films. And we typically grow in these films 1 atomic layer per minute. So it's a very, very slow technique. And when we in the MBE field say we're growing thin films, we're thinking of films which are only a few nanometers thick. In some other fields, a thin film is a few microns thick. And that would take days, well, not days, a couple of hours for us to get to those thicknesses. Right, but the cool thing about being able to grow at these really slow rates is that we have really good control of the defects in these systems. So we can grow films which are really atomically precise with really low defect densities. And during the growth, we can monitor the crystallinity of the surface using an electron diffraction technique. So this is an electron diffraction technique we can get during the growth to monitor the crystallinity and the symmetry of the surface. And after the growth, there are a lot of techniques we use to actually confirm that we've grown the materials that we would like to grow. So in this stack here, I'm showing you a high-resolution electron microscope image taken with some of the TEMs that are located here in Bill Center here, where each of these dots here represents a column of atoms. So you can see that these films are really, really highly ordered. The contrast you see here is when you go from the substrate to the film. And in the film, we can use the techniques in these electron microscopes, which allow us to also have more element specificity, where we can very precisely see that here we're growing exactly 2 chromium layers, and here we have exactly 1, 2, 3 layers of these manganese containing compound. All right, so we also have another system where we can grow the materials, and without bringing them out into vacuum, we can transfer them into a separate system here to do spectroscopy. Right, so besides epitaxial strain, we also have another knob we can use to tune the properties of materials. And this knob here has really come to the forefront since the discovery of this particular interface between a material called lanthanum aluminate, which is a very insulating material, it's a band insulator, and strontium titanate, which is also an insulator. So a couple of years ago, many years ago now, a group found that, so Otomo and Huang found out that when they grew this material, lanthanum aluminate, on this strontium titanate substrate, if they grew only a few, 1 or 2 layers of this material, the system was insulating, as you'll expect, because these 2 parent materials are insulating. But they found out that past some critical thickness of the material suddenly became metallic. The interface became metallic. And since then, people have found out that this interface between these 2 materials, which by themselves are insulating, is actually superconducting at low temperatures. So this is a millikelvin, but nevertheless, it's a really cool thing to think of, taking a brick and a piece of wood, putting them together, and having superconductivity emerging at that interface. But the reason this emerges, people have studied it, and there are many different reasons why this emerges. But the main understanding is that in this particular material, lanthanum aluminate, you can think of it as something called a polar material, because if you look at the charges of each of the constituent elements in each layer, so in this layer here, you have lanthanum and oxygen. if you sum up the oxidation states, it has a net positive 1 charge. And so there's this alternating plus minus charge as you increase the film, as you go from the interface with STO, which is neutral, up to the surface. And if this material gets too thick, the potential that you build up gets too large, it starts to diverge. And so the system, nature doesn't like that. Nature doesn't like diverging potentials. And so the system reconstructs by either moving charge from the film to the interface, or by creating vacancies, oxygen vacancies at this interface, or by intermixing this trivalent lanthanum with the divalent strontium here to alleviate this polar catastrophe. But the emergent property is that nature spontaneously gives us a system here which is superconducting and has some really cool and interesting physical properties. All right, so let me skip that. And so once we got the materials, we can image them using the electron microscope. But my background is in using synchrotron X-rays in many different ways to understand these interfaces. So one way you can use X-rays to understand the structure of a material is by X-ray diffraction. So you take your sample, you shine X-rays on it, the X-rays get diffracted onto a detector, and by measuring the intensity as a function of the angle, and you can reconstruct that to go back to get the structure of your sample. So this has been used for protein crystallography, and it's widely used in material science. The other thing you can do with X-rays, particularly if you go to an X-ray source like the one that Sean runs now, and Ken, and well, not neutrons, well, is that you can tune the X-ray, the energy of the X-rays to excite transitions in your material. So you can get really specific information, chemical information about your system. I'm going to talk about how we can also use this X-ray spectroscopy to get information about the spin, the magnetic properties of the individual elements in the materials that we fabricate. And the other thing you can also use X-rays for is direct imaging, where you take thin slices of your material and then you shoot X-rays through them. And this was some work I did doing my PhD work on some nickel-based superalloys for turbine engines. All right, so these are the two main sources that we use. We use the advanced photon source outside of Chicago. We use the hard X-rays there for diffraction. And we go up to the advanced light source, and we use the soft X-rays there for spectroscopy. And the technique that we use, that my group specializes in, is a technique which allows us to get diffraction data in 3 dimensions for films which are epitaxial with a substrate. And being able to go back from the diffraction data to a real space image is pretty challenging. But we've developed, we use a technique which allows us to do that, to reconstruct the diffraction data into real space 3-dimensional electron density distribution maps of our systems. So this is a non-destructive technique. And so we can take our sample, get 3D in reciprocal space. That was my former grad student, who is now a postdoc at MIT, at 2 in the morning on some day in the past few years. Anyway, so we go there for a couple of times a year. We get the data, we come back, we analyze it, and we can get these really nice, beautiful electron density distribution maps, which allow us to resolve the positions of all the atoms in our material in every single layer with sub-picometer scale resolution. And this is the kind of resolution we're going to need to answer some of the questions that I'm going to pose in the next few slides. All right, so going back to the LSMO case, it has a beautiful phase diagram. We know how it behaves when it's in bulk. But the question then is, if you would like to make a spintronic device and want to make a really thin film of this material, or take advantage of the fact that it's a metal and use it as an electrode in some all-oxide electronic device, we'd like to make this into a thin film with whose thicknesses are now going to be on the order of a few unit cells. And we're definitely going to be making an interface with this material and some other material. So the question is, what happens when you reduce the dimensions of this LSMO system? So if you grow a 30 unit cell thick film, each unit cell is roughly about 0.4 nanometers. So 30 unit cells is about 12 nanometers roughly thick. The film, and you measure its magnetic properties in something called a squid. At high temperatures, there is no magnetic response because it's in that disordered magnetic phase. When you reduce the temperature, going down towards, 2 Kelvin in this case, you can see that there's a magnetic moment that we can actually measure. And this saturates at a value which is very close to what you expect for bulk LSMO with this particular composition. So when you grow this material very thick, it behaves very much like the bulk film, even though it's strained to the strontium titanate substrate. But if you reduce the thickness by a factor of 10, so let's go from a 30 unit cell thick film and go a 3 unit cell thick film, we see that, and again, this magnetization is normalized to the thickness. So if it was the same property, then we should see the same type of curve. We see that this 3 unit cell film has completely lost all its magnetic properties. And this is a really common phenomenon in a lot of thin film systems where in some cases, when you make the material very thin, you lose all the interesting properties which you had in the bulk forms of these systems. All right, so this wasn't a discovery we made. It was well known when I was in high school. Well, I'm not dating myself, but that for LSMO films, if you grew them really thin, if they were very thick, they were nice, they had low resistivities. The resistivity went down as you reduce the temperature, which is what you expect of a metal. If you made them really thick, thin, so 5 unit cells, then the material became too insulating to measure even close to room temperature. And the same thing happened with the magnetic moment. So this was called the dead layer effect, where if your material was too thin, it was effectively dead, right? So what we like to do is understand why it dies and hopefully resurrect it from the dead. So going back to the structure, if we actually look at the structure of LSMO, it's very similar to the LAO-STO case where each plane here has some net charge. And for this particular composition, it's going to be a plus 0.7, minus 0.7 stacking in the vertical direction. If you terminate your material, which we can do pretty well with, for example, manganese oxide, then the layer at the top here has a net negative charge. So here you have a charged surface, a polar interface if you grow it on strontium titanate. And there might be some reconstructions which might occur here, which in this particular case are leading to the dead layer effects, whereas in the case of LAO-STO, we're leading to science and nature papers. Yeah. All right, so we took a 10 unit cell thick film, took it to the synchrotron, measured the structure as a function of layer, and I'm going to speed up here. But the main thing we found was that at the surface of these films, so this was a 10 unit cell thick film, which was above the transition thickness transition limit. We found out that because we were able to very precisely measure this atomic displacement, we found out that the manganese at the surface was displaced upwards relative to the oxygens by a very, very small value. So the displacement is plotted here from the surface to the interface with the STO. The displacement starts off by 0.2 of an angstrom, which is very, very small. But what we found here, which was significant, was that this effect was not just at the surface. There was a decay length of this distortion, which was on the order of 1, 2, 3, 4 unit cells. So if you count from the surface, there are about 2 to 3 or 4 unit cells which are distorted, which have this polar-like distortion. And then there were some other changes in the structure. But the main reason why these distortions are important, and we find out even if you go a 4 unit cell thick film, you still have a surface region which is highly distorted, is that the magnetic interactions, again, I told you about the bond angles, right? So if you now have this kind of polar distortion, you're also effectively changing the bond angle between oxygen, manganese, and the neighboring oxygen and increasing the bond length. And this is what we think is related to why these very thin films lose their electronic and magnetic cool properties. So the experiment we wanted to do was hopefully relatively simple. We said that if you have an LSMO surface and you have something neutral or vacuum on top of it, you're going to have this charged surface. If there's a negatively charged MnO2 plane here and there's nothing on top, then you're going to have a net negative charge there. But what happens now if you take another material which has the same plus minus 0.7 charge stacking and put it on the top and bottom interface of these very thin films? So the idea here is that if you have, for example, this manganese oxide layer here, is going to see a 0.7 charge on top and then 0.7 on top. So there's going to be no net electric field to drive these ions up and down in those layers. So we think that the main thing that was driving these ions and displacements were just the fact that you have an electric field that moves them around. So in this simple experiment, we chose to use lanthanum, strontium, chromium oxide. And we chose this material. So chromium is right next to manganese on the periodic table. You can also use iron or titanium, but you end up with charge transfer between these other elements and manganese, which ends up counteracting what you're trying to do. But we also chose LSCO because it's an antiferromagnetic insulator. So if we ended up finding that these materials were magnetic, we knew that it was coming from the LSMO and not the LSCO spacer layers. at that interface. So here we're going to try and change the electrostatic boundary conditions and see if it leads to recovering magnetism in the system. Right, so going back, a 2-unit cell thick film is effectively dead. Now, if we put some icing on it, so the icing in this case is a lanthanum strontium chromate, we're going to put 3-unit cells on the top and the bottom interface. We do find out that the material becomes ferromagnetic. We do now measure a ferromagnetic signal in these very thin films. So again, this is only 2-unit cells of LSMO, and then here we're able to find that there's a really appreciable magnetic signal we get in the sample. So the question then is, why is that the case? We can also change the thickness of the LSMO and keep the spacer layer thickness fixed. But we found out that as we change this this LSMO thickness and measure the magnetization, we found that the magnetization per manganese increased, and the transition temperature went towards room temperature as we increased the LSMO thickness. So what that tells us is that there's something else which might be happening here, which we're not accounting for in our very simple model. And in our simple model, we assume that the lanthanum strontium chromate was anti-ferromagnetic, so all the spins will cancel out and there will be no contribution to the total magnetic moments. So we took the samples to the the Berkeley advanced light source, yes, not the advanced photon source. And so here, the experiment we're going to do is we're going to put our sample in a magnetic field, apply a magnetic field in plane. We're going to use left and right circularly polarized light incident on that sample and measure the absorption at the manganese edge and the chromium edge, so we can measure the magnetism on the chromium sublattice and the manganese sublattice separately. And so when we do that, so in this experiment, you do this experiment twice with the left and right circularly polarized light. You take the difference. This effectively measures how much of your sample, the spins, density of states have an up polarization and a down magnetic polarization. If your material has no net magnetic moment, then these two, the blue and the red curve, are going to be the same. If your material has a net moment, you can see that these two curves are not the same, and there's a difference that I'm plotting down here, which, if you integrate, gives you a positive value. So the positive value you get here tells you that the spins in the manganese sublattice are aligned in the same direction as your applied magnetic field. In the case of chromium, we expected there to be no difference, but we found out that there was actually a difference in the intensities we measured for the two polarizations. And if you integrate that, you find out that this gives you a net negative moment. So what that tells us is that in this system here, the LSMO is ferromagnetic as we expected it to be, but the manganese here was forcing the chromium right across that interface to want to align itself in the opposite direction of the applied magnetic field. So this is something which is known as an anti-ferromagnetic exchange, where we can understand based on the orbital, the electron occupations, that why this is the case, why the manganese here is the one which is driving the chromium here to have a magnetic state, which is not what the bulk LSCO wants to be. All right, so we've confirmed using X-ray diffraction that if you have this sandwich structure, the distortions now go into the chromium oxide layers, and the manganese layers now have a bulk-like, do not have these polar distortions. And that confirms, I think, our hypothesis that these polar distortions might be what is driving this thickness-dependent transition in the system. All right, so we have played around with strain, and we've looked at the effect of strain, compressive and tensile strain by growing it on different substrates. We find out that for the very thin layers, if you have only 2-unit cells, there is no effect of strain, but as you increase the number of layers of the manganite in the superlattices will grow, we start to see effects that we can explain, which are related to the strain states of these systems. All right, so one interesting thing then you like to do is if you can change this polarization dynamically, then you can effectively make a switch where you can turn the magnetism on and off if you can find a clever way to do that. And there have been many, there's a lot of work which has been done using ferroelectrics on some of these oxides to modulate the charge and the structure of that interface to cause some other parameter change. But so we had a colleague do some DFT calculations for us, and he found out that the magnetic structure that we found experimentally was indeed the lowest energy state of the system, where the LSMO and the chromium spins are in opposite directions. But more importantly, he finds that very close in energy, even though it's a high energy state, it's a state here where all the spins align themselves in the same direction. So you can think of this here as a state where if you were to do a squid measurement, you'll be measuring the difference between the chromium and manganese moments, whereas in this state, you're going to be measuring the sum of the moments. So if you can jump between this state and that state, you can effectively turn the material from being have a very low magnetic moment to a really, really high magnetic moment if you can do this correctly. And you also expect this state to also be metallic because of something called double exchange, because of the parallel alignment of these spins. So we've been starting some preliminary work on this, where we've done some ferroelectrics on top, and we currently see a very small, well, it's a 20% modulation. It's not 100% as I would like, because we're using an 8-unit cell thick film. But we have some we're working on trying to reduce the thickness of this LSMO down to the 2-unit cell thick level so that we can actually get this 100% modulation in the magnetism in this system. All right, so very quickly, and you've heard about yes? Oh, 5 minutes, okay. You've heard about superconductors already. Everyone wants to get a room temperature superconductor and get it correctly and get it right and not fake data. So there's been a lot of progress over time, and there's been some really good work from the Mundi group here in discovering superconductivity in this nickel-based compound, which wasn't known to exist before. And one of the tricks there was, so lanthanum nickelate has a perovskite structure I showed you previously. And it was discovered at Stanford that if you reduce this, you took out some of the oxygens in some of the planes in the system, you can actually convert this material from being into a superconducting phase with TCs, which were close to 10 Kelvin. And again, Julie's group has also done some work in other systems here to show that you can reliably get superconductivity in these nickelate systems. So in searching for new superconductors, we can either make them in bulk or based on theory, driven by theory, or we can also go back to these interfacial superconductors and see if there's other systems where we can get higher TCs than 200 millikelvin. And one of the new systems, I'll skip this. But one of the systems which has been of interest in the last few years is the growth on this substrate called potassium tantalate, where in a very similar way to the LAOS GOKs, people have found that you can induce superconductivity at a little bit higher temperatures. It's not 200 millikelvin. It's on the order of a few Kelvin, which is progress, right? Going from 300 to 2, it's a really big leap. And by understanding how these superconductivity emerges, there's a lot we can learn to drive TCs to higher values. So another system we have started recently looking at binary oxides. So in most superconducting materials, at high temperatures, as you reduce the temperature, the resistance goes down, so it behaves in the metal as a metal. And then at some finite temperature, the TC, you end up with a drop to zero resistance state. Back in the late 60s and early 70s, there's a lot of work done on binary oxides, so niobium oxide, vanadium oxide, titanium oxide. And there were a lot of papers, well, a few papers from that era, which found that titanium monoxide, if you could stabilize titanium in a rock salt phase, you could actually get superconductivity a little bit below 2 Kelvin. So I think the TCs in the bulk was around 1.8 Kelvin. So around 2019, there's a report from Gayles where they found that if you grew thin films of this titanium monoxide compound, you actually could get TC as high as 6 Kelvin. And there have been more recent papers which show that you can push this TC all the way up to about 11 Kelvin. I haven't seen the 11 Kelvin reproduced yet. But one thing you see that's different here is that, first of all, you have to increase the thickness of the TiO to a few hundreds of, about 120 nanometers to maximize TC. And the resistance goes up before it goes down, unlike what you see in a lot of the other superconducting systems. So we've been able to grow these materials using molecular beam epitaxy. We've varied the oxygen pressure, we've varied the thickness, and we can get a wide range of interesting properties. We can also reproduce the same kind of up and down behavior. But one thing we also found is that under certain conditions, we can get films which are metallic and show a drop in the resistivity down to the lowest temperatures that we can measure in my lab. So one of the things we like to do is understand whether disorder plays a role in this semiconducting state. And if we can suppress disorder, then we can probably engineer superconductivity to high temperatures in the system. In the interest of time, I'll skip this to say that depending on the oxygen concentration, so in the cubic case can accommodate up to 25% oxygen vacancies without changing the structure much. But you can also engineer the oxygen ratio during the growth to get a wide range of other different phases. And some of these phases here are superconducting, and Ti2O3 is not superconducting. And so we're able to grow these materials under different conditions, get the different phases, and get all these different properties. And under certain conditions, for example, if you're around this phase boundary here, we can actually get materials where we have spontaneous phase separation. So this is a light microscope image of a sample where you can see these dark and bright regions. For a lot of the other materials, the materials are single phase, but if you're close to a boundary, you can actually nucleate the different phases in the same material. And if you measure the transport properties, you can see all these different transitions which correspond to the different phases present in the system. But what's interesting here, and what's motivating some of the work we're doing now, is that because you can have a coexistence of the insulating phases and the metallic and superconducting phases, then you can make something like a Josephson junction. You can make a qubit if you can actually make layers of these systems in well-defined ways. All right, so we've also been doing in situ X-ray diffraction at the APS before it's shut down, and we'll hopefully be going back when the light turns on again. But here we can actually grow the materials and use the X-rays from the synchrotron X-ray source to measure the samples during the growth. And we've applied this to measure the sample I showed you where you have a metallic to superconducting transition. And what we found here is that this material has a 1-to-1 ratio of titanium and oxygen, but there are vacancies of titanium and oxygen in the system where you have these ordered rows of this blue titanium vacancies and oxygen vacancies in the system. So in the cubic phase, the vacancies are ordered, and we think that this order might give rise to that insulating phase in the normal state. But if you can get these vacancies to be ordered and reduce this order, then we think that's what leads to the metallicity in the system. But the question then was, if we have reduced this order in this system, why isn't TC room temperature? It turns out that we found a theory paper which did calculations, so you can calculate the electron-photon couplings in these materials. And what they found again here was that for this monoclinic phase that we find experimentally, the electron-photon coupling is relatively weak, and the TC that they predict is actually very close to what we think we're observing experimentally. But they also find some other phases here where if we can reduce this order, we can potentially increase TCs, for example, in this phase, up to temperatures above 10 Kelvin. All right, I will end here just by saying the interface is still the device. And you've seen from a lot of the talks previously that the interface really governs how these devices function. And as we think of quantum device, making the next round of quantum computers, which we can put in our cell phones, we really have to understand the interface and engineer them pretty well. So thank you very much.
Let's thank the speaker, Divine. And we have some minutes for some few questions.
All right, thanks for a Divine talk. So I have a question about your polar metal. So it seems that you've managed to create a polar metal.
Right.
One is, have you been able to switch it? And then the other is sort of related to this, which is, like Harold Huang's group has also done these liftoff techniques, right? And so if you lift off, does this polar rumpling go away?
We haven't lifted off, and I was going to talk about that, but I was out of time. And one of the things we're thinking of is liftoff and do an experiment on that. So no, we've not done liftoff. Yeah.
What about the switching of the polar metal?
So for the lanthanum nickelate system, when I was doing my postdoc work, we did show some switching in that system. We are currently working on the LSMO case, and maybe in the next few weeks, you might have some.
Thank you. I know it's a bit unrelated, but question: seeing how that you can change whether it's polar and it's a polar metal, do you realize optical phonons in this, like strong optical phonon coupling? Is there a Rastrolin band, and can you actually utilize that, like turn on and off like interesting optical properties?
That's a very good question. We've not done it for this system, but there's quite a bit of work being done in these oxide systems where they're actually trying to use light to induce both electronic changes and structural changes, which will change what the phonons look like. So, but yeah, the fact that it's polar means that we have that coupling we can think about playing around.
Right. So you can actually turn on and off the Rastrolin then.
Right.
Potentially.
Yes.
Yeah.
Thank you for your talk. It was great. Yeah, I have a question about. I am not sure if you looked at the charge density on materials before. I remember you saying that like when you grow your compounds, you try to be very precise and try to be as free of defect as possible, right?
Right.
But we know that like charge density wave can like live around the local defects, even at room temperature, right, way above TC. And I'm wondering if there is a similar mechanism with the superconductivity that can live around the defects.
Right. So in some of these compounds, without defects, you can have charge density waves. So the cuprate, for instance, the nickelates in the insulating phase, you can have a distortion of those octahedra called a breathing mode distortion, which can actually also lead to charge ordering in these systems. So there's a lot of work done studying charge ordering in these clean systems where you don't need defects to create that charge density.
Okay, thank you very much, Divine, for your divine time. And feel free to engage the speaker in the lunch session. Now, the last speaker for this morning session, Professor Jacob Gayles, he got his PhD at Texas A&M University. He's a theoretical and computational physicists. So in his PhD studies, he focused on topological systems and topological order. Then he did his postdoc in Germany, Max Planck, where he looked at skyrmions. These are two frontier areas of condensed matter physics these days. Now he's a professor at University of South Florida, studying chiral properties of materials, which have a lot to do with symmetry. So he's won awards, including, I think, recently the Young Investigator Award from the Air Force. So we welcome you, Jacob.
I think I'm going to try this side because that's not been so much on this side. But thanks for the invitation, and it's been a very great conference. And it's been very nice to speak with everyone, and I'm happy that I had to go at this position in the conference because a lot of my work has been done for me. One part that is, I think, very interesting is that there's a common theme that goes throughout most of the materials talks, and this is the idea of disorder or defects that we've been talking about, and that we actually want these things to happen in materials, right? Which is kind of strange because they're called defects. You would think you don't want them. So we saw this in the nitrogen vacancy centers that turned the diamonds pink. For Serena's talk, we saw this actually helps stabilize these vortices, and now in Divine's talk, he broke this crystal symmetry order by making these interfaces. And so as a theorist, this is, I had a discussion with someone the other day that this kind of sucks, right? Because our idea is dealing with this perfect Hamiltonian, which has these block waves, which we'll show later. And now if we start adding impurities and things like this makes our Hamiltonian much larger, very hard to diagonalize. And so this is what we'll be talking about, which is this working? Okay, so interfaces in quantum chiral materials. And this idea was called a Skyrmion, which is this magnetic texture in real space, and a Weyl system, combining that, which is a magnetic texture in momentum space, and how we use that for efficient spin manipulation. Some of the funding comes from the Air Force, Max Planck Partner Group, and the Control Scholar Foundation. So firstly, this may have been asked many times, what are quantum materials? Any student want to try and give a guess of what this is? Anyone has a concrete idea yet? So I like to think of, as a theorist, computationalist, I like to think of things very simply. And so my idea what a quantum material is that the whole is greater than the sum of the parts, right? And so this idea is where these synchronized swimmers come together. By themselves, they cannot make any of these structures. Together, they do. And if you take it one step further, you can look at the patterns of these waves that form. This would be the electronic wave that has the properties of that crystal structure. Okay, so now we have to go back. Divine said this was a new field. I've been in this field almost 20 years since I first met Sandra Jones. So it's called spintronics. And there's two ideas that come in here. One part is controlling the charge of material, or the charge of electrons in a material, right? And so that's done very simply. If you know your classical electrodynamics, you can control the charge with an electric field and a magnetic field. And that charge has to be moving to be controlled by a magnetic field. And this produces what's called a Hall effect. This was done in 1889, where you have a perpendicular magnetic field and a perpendicular electric field. This causes a voltage that's perpendicular to the original electric field and the original magnetic field. On the other end, you have what's called the Stern-Gerlach experiment, and this is when you have a non-uniform magnetic field. You produce a splitting of, if you have, in this case, fermions, spin up and spin down. So that's the most basic way to control charge and the spin. And the whole idea here is how do we combine these two, right? So how do we combine this to make quantum devices such as quantum computers, where we can control these spins, and how do we control the charge there? Good. Hopefully I can convince you that we can do this, at least from the theory side. So quantum materials have a big umbrella. Of course, one is the quantum computers, these with the dilution fridge we've seen earlier, graphene, we have solar cells, these germanium sensors to detect dark matter, light-emitting diodes, lithium-ion batteries, these magnetic disk hard drives, and of course, quantum dots, which was talked about a lot. I will focus on this area of materials here, which are this graphene type materials and these magnetic materials, and try and combine the two. So the outline is pretty simple. I will start with some introduction. I'll spend most of the talk here in the introduction, just so you know, and then I will go, just because I'm a theorist, I have to show you the Hamiltonian. There's no Russians in the audience, but if there were, they would be happy. And then I'm a little bit different than the rest here. I'm going to go over very quickly some of the results in our lab that's not published yet, but I think this is a trustworthy audience, so it should be okay, yeah? They're close to publication. Good. So let's talk about the old way. This is how my predecessors thought about materials. One is you have to start with some wave function, which depends on K and depends on some distance in space. You have some phase factor out in front, and it looks like a plane wave. If I forget about the potential for now, then the Hamiltonian is very simple. I'm looking just at the gradient of that wave function, and that's going to give me some energy eigenstates that depend on K, and it looks like a parabola. It's very simple. I think everyone understands that, right? And then here I actually have two lines there. They're right on top of each other if I can include the spin in there. So spin, because there's a fermion, they lie right on top of each other. Then I can start to add a periodic potential in here, and what that's going to do is just going to open up a gap in my system, right? And this energy gap is something interesting because it's going to distinguish what type of material it is. Because you have fermions in here, they have to fill these states in a particular way. That means they go in one by one, and they cannot land in the same state. Then what I can do is I can use, I can count how many states I have, and that's called the density of states. And at low levels, in this case, I just have 2 states. In the gap, I have no states. And depending on how I fill this, I use what's called Fermi-Dirac statistics. It's either going to be a metal if I'm below the gap or above the gap. And if I'm in the gap, it's an insulator. Okay, so let's go a little bit further into that density of states. This is a more simplistic view of it. So if I have a metal, I have below and above my Fermi energy, which is my Fermi-Dirac statistics. I have states. I have a finite number of states. directly at this red line. So that means I had need a very small amount of energy to go from below this red line to above this red line. So that's this idea where I tell my 7-year-old son not to put the fork into the outlet, right? Because it's a very small amount of energy for it to conduct. Then we come to, the holy grail of the past, few decades, which is a semiconductor. And opens up a small gap. And that's due to this periodic structure where electrons pile up on the edges of the Brillouin zone. And you have a small gap here. And you can excite electrons across this gap. This is where Desi was showing that you have this little bit of lightning that goes across. And you can excite electrons above where you have an electron that moves down in this conduction band. And the band below, you have what's called a hole, right? So it's a missing electron that's moving around. So it's like an empty seat on the bus. Who's going to sit there? And then lastly, you have what's called an insulator. And in this case, the gap is very large and it's almost impossible to excite electrons to that next level. Good. So the theory for this was done a while ago, but graphene came and changed the game drastically. And one case is not only did you have to use physics to understand these materials, you have to use also chemistry. So what graphene has is these carbon atoms, which are made of S and P electrons. And so the S electrons and the PX and PY, they hybridize and they form this covalent insulator type bond. So no longer do I just have purely an insulator or purely a metal, I have some mixture of it. And then you have this PZ orbital that kind of floats around freely because it doesn't have anyone to interact with because of this chicken wire or hexagonal net that's made. And that becomes a metallic case. And so when you look at the electronic structure of those bands that I showed earlier, or that diagram, the low energy dynamics of it becomes linear. And that's looks exactly like the Dirac equation or the massless Dirac equation. And there's two spins there. I got the Nobel Prize in 2010 from Andrew Geim and Novoselov because of the Scotch tape method. And that's what really boomed the field back into this idea of, okay, we need to look at the electronic structure differently than just this simple insulator metal and semiconductor. And this is actually called a semi-metal because of this touching of the bands. Good. And so after graphene came was this idea of what's called a topological insulator. What you start with is you want to invert those bands, and then you add something called spin-orbit coupling. Spin-orbit coupling comes from this Dirac Hamiltonian, which is just a perturbation of this or low energy extension of the Dirac Hamiltonian, where your spin is coupled to the orbit, right? And so your spin has a certain direction as it moves throughout space, and that's exactly what we see with this phase locking of the moon or going around the Earth. And so on one end, you have what's called a topological insulator. And so this is a completely different type of material than what we had in the old days, where a bulk material or infinite material of this is completely insulating. Now, to make it topological, you have to cut this material. Once you cut this material, it's interfaced with a different material, which is vacuum, which is also insulating. But these are two different types of insulated materials. And for this perturbation to work, you need to flip the inverted bands. And in doing that, you create a metal only at the interface. So it's the same material throughout, same characteristics throughout, but only at the interface do you have this conducting band. And those conducting bands form a Dirac point. Now, from there, what we can say is let's squeeze this material down to the smallest 2D layer. And this is just a metaphor, but we squeeze it down and then stack a bunch of them up, we can form a line of these Dirac points. And that's what's called a Weyl semi-metal. So you have a line of these Dirac points, and what happens is it cuts your Dirac cone on your surface in half, and what you get are these two what's called Weyl points that exist in your material. What's nice about these is they still have this linear dispersion, so they have very high mobility. You can use them for a lot of different types of electronics, and they still have also these very nice surface properties. And they're topological when you calculate this, and we'll get to that more later. 12:30 we want to finish, right? For lunch, just making sure. Okay, so since that's come, there's been a whole zoo of these Weyl semi-metals. So the first one I showed was this 1 plus or minus 1/2. You also have some other cases, which is where you have a plane in between, you have plus or minus 2 charge, and you can also have double Weyl fermions. The way you count them is you're looking at the spin, so the spin of the electron in momentum space and how that evolves, and you have to always do this contour integral in the imaginary plane, of course, to get counted, and you always have to go in the same direction. What's important for the Weyl points is what's in between. So what's in between there is what's called this barrier curvature, and that produces what's, what we saw earlier, this Hall effect, but the quantum version of this was this anomalous Hall effect, and that's due to this internal magnetic field of the system. And this is just a very simple picture showing this barrier curvature that comes out and how the spin of the electron changes direction upon seeing that magnetic field. So it's a spin-dependent magnetic field that comes out. So let's go to the other end. I think we all understand the Weyl materials now. Good. All right. So let's go to the other end now. Let's look at magnetic materials. If we take a single magnetic atom and look at the local density of states just for that atom, we can split up the density of states into two, right? So we can split up the density of states for the spin up and the spin down. This is the metallic case here. And that produces a local magnetic moment. And when that is on all the atoms, then you can have some ordered magnetism throughout. That creates some exchange. So if the exchange is positive, depending on how you write your Hamiltonian, then you have a ferromagnetic case, meaning all the spins want to line up. And if it's negative, you have what's called an antiferromagnetic, with the Devine spelled out very nicely for us. Then these spins alternate for each nearest neighbor. You can have many things in between. So what you can have in between is that the moments can be different sizes, and this is called a ferromagnetic. And lastly, this new thing, which I didn't put on the slide, which is called this altermagnet, and this is connecting both the real space and the momentum space texture of the momentum vector, but we won't go into that. Why is this important? So this, for me, I think is one of the things that got me into science was understanding this idea of the giant magnetoresistance. So if you have two magnets, I can line them in the same direction and pass a current through. And when they're in the same direction, I have a very large current that goes through. When I change the direction, I can reduce the current to 0, and this creates a bits of 1 of 0. The reason why that's interesting, this is right around the time I was born. The amount of information was stored analog, right? And so this is everything that was, started from the Gutenberg printing press, everything was printed. And right around 1987, Peter Grunberg and Albert Fert discovered this idea of giant magnetoresistance. And what happened here is that the information became to be stored in a digital way, and it jumped in the amount of information we had. And this is important because that changed the equity for people to access information, the same as the Gutenberg printing press did. Good. So the magnetic interactions, which I won't go into full detail, we have the exchange, which I explained earlier. We have what's something called a DMI. Now this is a bit different than the exchange. This is the chiral interaction. Maybe I can write it down because it's a little bit easier to see when you write it down. So we have this HDMI, which looks something like the sum over ij, 2 spins. And we have D, which is a vector here. And we dot that into Si cross Sj. I can put ij here for the sum over each neighbor interaction. This here is this is what drives the chirality of the system. So if I change the sign of D, that means I have an opposite chirality. And it wants the spins to point perpendicular to each other. All right, so either they're going to be perpendicular like this or perpendicular like this. So it has another added factor than the exchange, where the exchange is just a tensor. This is a second rank tensor here, the DMI. Now, what's interesting here is what happens when these two terms compete. So one wants things to point parallel or anti-parallel, and one wants perpendicular. What you get is Goldstone modes or spin spirals or magnetic textures that come out. There are other terms such as anisotropy, which wants all the spins to point in a certain direction, or the magnetic field in a similar case. You also have dipole-dipole, and you also have 3-spin and 4-spin interactions, which I won't go into. What it looks like, which I explained earlier, is the exchange, which is a positive exchange, same direction or opposite direction. The DMI is a vector direction, so this is going into the board or parallel to the board, changes the direction of spins, and then you have dipole-dipole interactions, and you have 4-spin and 3-spin interactions. The energy scales determines what kind of magnetic texture you get out in the end. So the highest usually, so this is just arbitrary, and this was the reason I put these numbers up. This was a very easy way to use the decascale to show how you get a skyrmion. Here, exchange usually this is what it would look like for iron, which will give you directly the Curie temperature, right? So this is the transition from being ferromagnetic to a paramagnetic. Then the DMI, if you break inversion symmetry and you have spin over coupling or spin image coupling, it's usually around 10 MeV. And anisotropy is usually a bit lower, but it can be on the same size as DMI and interface materials and two-layer materials. And then you have dipole-dipole, which is usually very small but very long range. And then lastly, you have these 4-spin interactions, which are usually small, except for when you have large magnetic moments. Good. And so what these skyrmions look like, what happens when you get this skyrmion, this is called a magnetic texture, where at the center you have a definite direction of your spin, and on the outside it's completely on the infinity. Depending on who you talk to, if you talk to the pure mathematical people, on infinity it points in the opposite direction, and there's a smooth variation in between. This part that it being smooth is very important to the discussion of topology. If I take a square here, a line, this gives me one of these nil domain walls. And they have another type of skyrmion, it's another type, but it has the same topology. And this is called a block skyrmion. And so this one, if you look at the domain wall here, it rotates in and out of the board, where this one stays in the board. And then lastly, you have what's called an anti-skyrmion, which is a mixture of the two. And this one actually winds in the opposite direction, meaning that the topological charge actually changes in this one. What this does, and the winding you can measure almost exactly the same as you did for the Weyl semi-metal. And what this does is it produces a magnetic field. And the magnetic field is determined by the size of it. So it's a very local magnetic field. So if I make my skyrmion smaller, I have a very large magnetic field. If I make it bigger, I have a small magnetic field. But what this does is winding, when I change it, it will actually change the size and the sign of my magnetic field. So it's also a way to have a bit of information, and it's nice because they can move very quickly in materials. They have a very nice response to currents, I should say. And there's also a skyrmion zoo. So, you have also, I showed the anti-skyrmions, you have what's called an intermediate skyrmions, you have higher order numbers that are larger than plus or minus 1, you have bimirons, you have biskyrmions, where there's 2 skyrmions, ferromagnetic skyrmions, synthetic antiferromagnetic skyrmions, you have bobbers, and also now the new big thing is called this hopfion, which is a 3-dimensional skyrmion with a different type of topology. Maybe I can ask you questions for the students here. Can I ask a question? Who wants to try and answer? So Serena earlier showed a vortex. Can anyone tell me what the difference between a vortex and a skyrmion is? So here with the vortex, what happens is it doesn't have that well-defined center, right? And so the vortex is, for the most part, in plane. They do couple to skyrmions. I think Serena knows a bit more about that than I do. But they also have interesting properties. Did you have a question, or you can ask?
So I'm a computer science and mathematics major. So here I'm looking at all of this, and I'm just wondering, what causes? I was listening, but what causes all?
I was trying to listen. Yeah.
What causes all of this to have different shapes? What changes the topology?
That is an amazing question. I have one more slide, I think, before I get to that.
Okay.
That's very, very nice. You should be a theorist in physics. Very nice predictive abilities. So it's skyrmions. I kind of talked about this already, but you have a very nice response to this to currents. One aspect is you get a Hall effect, like I explained earlier, because there's a magnetic field. The electron, it's an internal magnetic field, which acts different on each spin, and so these spins will require also again this barrier curvature. But now this is a real space barrier curvature, different than the Weyl semi-metal. And because you want to conserve momentum, you also get an effect that you move the skyrmion when you reach critical currents. What causes all of this, right? And so this is symmetry that causes all of this. This is how you change these different materials. So if you have the break inversion symmetry for a skyrmion, you need to break, well, you don't need to do it anymore, but when we started, it was you have to break inversion symmetry and time reversal symmetry. When you break time reversal symmetry, you get magnetism. And then breaking inversion symmetry allows for this chirality dependent term to show up. So you get a left or right handed chirality depending on how you break inversion symmetry. Similar case for the Weyl semimetals. It's a little bit different here. You can break either inversion symmetry or time reversal symmetry. And that gives you different types of Weyl materials. Yeah. So does it answer your question? Yes. Good. Now we're getting closer to the end. I will try and make it by 12:30. The idea is now we have these Weyl materials which couples the spin of the electron to some momentum vector. And that's the picture we showed earlier. This is a three-dimensional image of the Weyl, and that's the low energy dispersion. And then on the other end, we have the skyrmion, which couples the spin of the electron to the magnetic texture. And our goal is, how do we mix those two, right? Can we combine those two in one material or some cases of materials? And then what will happen when that happens, right? And so one case is when we look at skyrmions and the very small limit, or I call in this case, the strong coupling limit, depending on how you look at it. And in this case, what will happen is you can control both spins simultaneously. In the other case, in the large limit or the weak coupling limit, the spins of the electrons will diverge. And of course, the big interest is what happens in the middle, which is the hard physics, right? What you can see is here, these are actually some results from my PhD, is that what started a lot of this is that some of these materials, which we're not interested in this part in my PhD, but the Weyl actually pops up here, and that's where you get the largest topological Hall effect for these materials. And then also when you with the skyrmion, when it affects the Weyl, you can open a gap. And because that gap is inverted, you get what's called this quantum anomalous Hall effect, which Pablo Herrera talked about a lot. And that's also nice for computing devices. Good. And last thing, of course, is to manipulate the spins. Because these Weyl materials, this momentum vector here is essentially your current, right? This is your internal current to your system, but when you couple the spin to it, you produce spin currents, and that is the most efficient way to manipulate these skyrmions. So there's a lot of different avenues one can go here. So my goal, of course, is two-part. One case is to look at these magnetic textures in the bulk, so combining the skyrmion and Weyls in the bulk. And this is more just for the exercise of understanding what's happening and how they combine. And the other end is for the application side, of course, is to combine them in heteral structures, so having a Weyl material below and a skyrmion material above to manipulate them in different regimes. Good? We finished the first part of the talk. Let's now go to the simple Hamiltonian, which we'll explain some of these things in more detail. So simple Hamiltonian is pretty straightforward. We have first I explain this term, which is essentially that h bar squared k term that I showed earlier, which is just hopping. It's just the motion of the electron throughout the lattice, which is connected to the spin here. I can have some magnetic texture there. And then lastly, I have some spin orbit coupling term, which couples the spin directly to the spin direction directly to the momentum direction. This Hamiltonian is very easy to diagonalize. And if I look at it along the path in kz, then I can get the cases where it always has to have this degeneracy of this Weyl point, which is bounded just due to this arc cosine here. And what happens here is when it's bounded and has these degenerate crossings, you produce an anomalous Hall effect directly at those crossings. And it's chiral here, so if I switch to chirality, then I switch the sign of the anomalous Hall effect. So that's what happens here. So, this is the case when I have the first band inversion, I have this anomalous Hall effect. When I switch to chirality, I change the sign of the anomalous Hall effect. This is a very nice property, right? So if I change the crystal structure, I can change the anomalous Hall effect there. Now, of course, one of the big things which was the trouble in my postdoc, was find how to increase the size of this anomalous Hall effect, right? And what happened was we were mostly here for most of the time. And so what happens is you can add more bands in, and if you change the chirality on one band that's opposite of the other, then essentially you get a canceling effect. Yeah, and so then what one can do, so if you want to systematically increase the size of this anomalous Hall effect, if you're interested in terms of the devices, then you can enhance it by using the same chirality. This is completely inherent to the symmetry of your crystal. Okay, good. So now let's go to some of the results of the students. This is a student on a Fulbright in Germany, and also a previous postdoc here where we looked at these chiral compounds, which I'm going to explain shortly. So in here, what we have looked at are these crystals called B20 compounds, which inherently have, the crystal structure has a chirality. And it has a left-handed and right-handed chirality, just like DNA. And so that chirality imprints onto all of my properties, such as my exchange, my DMI, my Weyl semimetal. When it's non-magnetic, I get one of the best Weyl semimetals that we've found, yeah? And so what happens here is this is the band structure for this material, depending on which compound you're looking at. You have, without spin over coupling, the spin 1, and then you have this double fermion that I showed you earlier. And then, like I said earlier, it's what's in between that counts. These are the Fermi arcs, or the in-between stuff that we're interested in. That's what causes the spin current and can use to manipulate skyrmions. So my postdoc and student did a bunch of calculations on this, and so this is for what's called cobalt germanium. And we looked at it without spin-orbit coupling, which reproduces the previous results. And then as we increase spin-orbit coupling, we produce those Weyl points, and we can see systematically here, this is the case for experimental result, but as we systematically increase it, we keep those Weyl points throughout. Now, then the next step is we have to add in magnetism, right? Because we want to have that skyrmion with the Weyl points. And that is also the case here. We keep those Weyl points when we add magnetism. They start to move in momentum space, but we're able to keep those Weyl points throughout. And then here, I'll show you quickly the Fermi arcs with spin-orbit coupling for the different compounds, which stay there. And the main thing we want to see is that, so in this direction, going down, we increase the magnetism, and in this direction, we increase the spin-orbit coupling. So the take-home from that is, and this becomes much more important towards the end, but we'll come back to it. By changing the spin-orbit coupling, we can increase the distance of the Weyl points, or change the distance of the Weyl points. And one thing that other happens, and this particularly in this system, is when we add spin-orbit coupling, we actually move the Fermi arcs away from the Fermi energy, which is not such a good thing, because we want that to be the main source of transport. However, when we start adding magnetism, we can also change the distance of the Weyl points, and then we also break down those unconventional fermions, which is spin 2 and spin 3/2, and we can also move them in momentum space. And they move back up closer to the Fermi energy, which is a good thing. Good. So we take a break from the cobalt germanium, this chiral compound, we come to what's called cobalt 310, which is this Kagome material, which has this, it looks very similar to graphene, but it has a hexagon in the middle and stars, triangles on the outside. And so this is, when I started my postdoc, the first week, my office mate wanted to find skyrmions in this material. And what I did was I looked at the symmetry and I said, not possible, it doesn't break conversion symmetry. And so I was off the project there, but then what he did find was those Weyl points in the material, and it became a very big paper in a very nice Nature Physics journal, and has done very well for material. However, recently, some people have found this red spot here, which is called this A phase or anomalous phase, where they look at the magnetic susceptibility. That means the change in the magnetization with the change in the external magnetic field. And they do this with AC fields and DC fields. They find this pocket where it looks like there's a magnetic texture. So what happened there? So the main thing that we said earlier, right? You need to break both inversion symmetry and time reversal symmetry to get those skyrmions. And this cobalt 310-2 does not do that, right? However, I have a very, dedicated student, and his idea was that we break that inversion symmetry by just chemically changing the atoms there. And so we did this, but one thing that we did was we looked at the magnetic textures in this material to see how the well behaves. And so at very low cases, it behaves like a Weyl material, what's called a Weyl semi-metal. As we start increasing the spin spiral, this is also increasing the temperature. We get a phase transition to a type 2 Weyl semi-metal. And as we increase it further, we gap it completely because there's a magnetic field there that gaps the electron states there. And then we also get these flat bands, which are known, but also very interesting. Maybe I ask another student to the undergraduates, we have like 5 more minutes or so. What kind of phase transition is this first one? Does anyone know? So the first one is what's called a type 2 phase transition because it's a smooth transition. The second one is a type 1 because it's distinct, right? Good. It's very important if you do quantum. Good. So he's mapped this for a lot of the compounds. So he's looked at the distance of these Weyl points and the energy of these Weyl points as a function of the spin textures. And he finds that it actually is very stable, which is a good thing for us because we want to not destroy these Weyl points with a magnetic field. This here is just the exchange that he calculated for his materials, which behaves nice as a test to make sure that it behaves with the experiments. And then here is the DMI, which is not a graph I would normally put, but it's actually not very large. It's not very interesting. It's not large enough to stabilize skyrmions. So then the next step was, okay, what's wrong there? And so we looked, which was my original prediction. So then we said, okay, maybe the DMI is changing layer by layer. So we had to write some new code to look at it layer by layer. And in the end, when we looked at it layer by layer, what happens because of the characteristics of those Weyl points, they suppress any energy that will give rise to the DMI, which is this is a DMI energy for each of those bands. And what you see actually is that it changes sign on both layers, and so then that also cancels it out. Still not enough to stabilize skyrmions. And so what we're working on now, which I don't show the results because I'm not completely happy with them, but it's actually a second order interaction that happens here that's similar to the DMI that actually stabilizes the skyrmions. Good. All right, the last one. The last one, sorry, there should be some crosses here. We're working, now we want to go to the interface, yeah? And this is a particular type of interface where essentially because these materials are chiral, we want to just switch the chirality on this interface. So it's just a crystal domain. It sounds pretty simple, something that you don't want, but we get very interesting properties come out. And the reason why that follows a cobalt 310, this is the discrete limit of that very long wavelength spin spiral. We have 3 limits to look at here. We'll only talk about one today, just to save time. So there's 3 limits where one case is where we have a very thin skyrmion layer, and that's what happens here. You have a very thin skyrmion layer and then very large Weyl materials on either side. And the other cases you can look at, of course, is where you have a very thin Weyl layer. That's where you get this gap opening, get this quantum anomalous Hall effect. And you also have these cases where they're comparable. So one thing that happens here is very interesting that we talked about earlier is if we take the cobalt germanium, pure, has no magnetism in it. When we create this interface, there's actually a finite magnetism at the interface due to this breaking of this structure inversion symmetry you have there. And we go back to, I like to be poetic, and so I go back to my previous Hamiltonian I use. And it's the same Hamiltonian, the only thing I'm doing now is I have this step function where on one side of the material, I have one chirality for my Weyls, and on the other side I have a different chirality. And then I can add some potentials at the interface. So this is very far away from the DFT. This is more a linear model, and we're just looking at the scattering theory that goes there. And so that's what it looks like. We change the chirality of these Weyls. We have one here and a different one here. And what we see is that this blue curve here is that Weyl dispersion that we had before. But what we get new is here at this interface, we get these bound states. And these bound states are topological, meaning that they're very hard to destroy. And we get 2 of them there. So I'll let you think about why that's interesting because they have also some spin characteristics there. That's the plane cut of these states that we have. So that's the Weyls here, and then they connect between the brilliant zone and throughout the brilliant zone there. And the other aspect why this interesting is the last slide of physics. The other aspect of why this is interesting is you can actually make very nice spin filtering devices. So when you have some magnetization texture at the interface, you can allow all the spins, and when you change the direction, you start to block spins that go through. So it's almost like just like this giant magnetic resistance that I explained earlier without any magnetic, ferromagnetic materials. Good. That's it. Oh, well, I'll skip this slide, but this was just proving, that was all, pen and paper theory. This is just proving that we can actually do it in these iron, cobalt, germanium materials, which are magnetic. That shows the wow, and then it shows the stability of these materials in terms of energy, and then also shows that we can also change the amount of spin-over coupling at the interface and the magnetization of these materials at the interface. Good. That's my group. We're hoping to expand here. So if you're interested, please let me know. And also increase the diversity there, we need to. And this is the group of faculty in USF, which we work with on, it's called Field QM. We work on low dimensional materials, my collaborators over the world. And then at USF, we have a very nice graduate program, which is located right here in the beach. If you're interested in the beach. My group particularly, we hardly ever spend the summers in Florida. So we try to go to Europe in the summers because it's too hot there. But what's very nice about this program is that it comes with, this is an applied physics program, it comes with an industrial practicum where you spend 6 weeks to 3 months working in an industry partner for your PhD. So that's actually required to get your PhD. You can't not do it. And yeah, we have a very nice new building, very beautiful campus. I actually, I consider myself a high energy physics in the building because I'm on the top floor there. But yeah, that's it. We also organize a conference. If you want to know about it, it will be held in Tampa. I'll probably send emails to some people to come. If you're interested, let me know. There's references for the talk, and thank you for listening.
Yeah, thank you very much, Jacob. We have some hands here with those gentlemen. Perhaps.
Do you study the shearing of Skyrmion lattices?
Do I still do the shearing?
Do you study the shearing?
Oh, yeah, for strain, yes, that's a very interesting case. I mean, so one is that with strain, you can change the size of your DMI. And of course, strain happens in a lot of these systems. I just kind of left it out. Actually, how you would stabilize these systems is not really been developed experimentally. I'm discussing with a friend, but you would have to grow them under strain and then remove the strain so they would relax back, which is not a simple feat. But yeah, study under strain is extremely interesting, yes, I would say. Because, I mean, what's very interesting for me is that there's an under strain. It doesn't matter if you do 20% or 0.5%, right? That symmetry is the same, right? You can't do 20% strain in an experiment, but that symmetry is the same for me. So as soon as you turn it on, it turns on. And that's kind of effects I like, that you can turn on and turn off very easily. Yes, next. I hope I answered your question.
Hello, I'm Alejandra Ponte. I'm going to take a little jab at you because you say South Florida, but I'm from FIU. So I'm real South Florida.
I mean, when I got there, I was thinking it's going to be much more south, but there's only alligators beneath this, so.
Yeah.
In Miami.
I guess I'm an alligator. I wanted to ask about you as a Florida native. The ongoing quantum efforts to broadening the impact in that sense. So at FIU recently, our best AMO scientist got poached, and it seems like it's a constant ongoing battle to put these types of scientists in our communities, especially for the one that you mentioned, the field one. Do you guys see some near collaboration in any time, or where you're looking to take some, for example, McNair researchers? I'm a McNair fellow myself, and we don't necessarily have all the facilities at FIU. So perhaps that type of collaboration between South Florida. Do you guys see envisioning it in the near future?
You have a very, very good question. McNair, so the McNair, we tried it, and we actually talked to you guys a lot, but we didn't get it, unfortunately. And then we also tried a Mercek, that it also didn't happen. So, I mean, of course we're interested in it. I think the trouble is USF is quite young, and so we still got to get some traction there. Of course, we're trying some quantum initiatives and things right now. We have a quantum certificate that's starting. We're reorganizing some of the graduate courses and the undergraduate courses. For me, though, it's a bit different because I am not tenured yet, right? So I have to wait till I get that, and then I can try and reach out more, right? So just have some security to do that.
Thank you. Wonderful. And by the way, the reason is we have a new director of the McNair program.
Yes, I know.
So we can talk later.
Yeah.
So one more question.
I was also a McNair student.
Thank you so much for the great talk. I was wondering how you deal with electron correlations and if the results you presented depend on the size of the system.
How do we deal with electron correlation? Yes, that we don't deal with at the moment. We are one electron type of group, right? At the moment, that's a tough thing to do, right? Because to train a graduate student in that, you have to first do 1 electron and then do 2 electrons. But
Okay, so the next question. So
it is important though, because we do have a lot of these flat bands that I kind of gloss over. But yes, it is not like it's not important. It's just training wise, it takes time.
So, you talk about symmetry breaking, right? So
I would never call it symmetry breaking, though. I would say a lack of symmetry, right? You don't go in and break the symmetry. But it's semantics.
So my question is, what are the symmetry of the Hamiltonian? What are the symmetry that preserve?
The symbol Hamiltonian that I have. This one? This one, you mean?
Yeah, what are the symmetries?
So this one breaks time reversal symmetry. It has C4 and it has C2. That's it.
Okay. So, the reason I'm asking is because
This one does not break inversion symmetry.
it's. I used to be very confused with this. Why some systems break symmetry, the other do not. But eventually, theorists explained to me that there's always a combination of symmetries that are preserved. You can break one symmetry at a time or two, but there's always a combination of symmetries that are preserved.
Not exactly. So if you want your DMI to exist, so there are crystals that break conversion symmetry, but they don't have any DMI because you have a rotation and an inversion that brings it back. So with DMI, you need 2 symmetries broken, right? So did I show it here?
Yeah, I think maybe we'll pause here and you can have a more one-to-one discussion, right?
Yeah.
I think everybody's waiting for lunch.
Sorry.
So let's thank Jacob again. And
thank you.